Our next speaker will talk about beyond recursive proving for Starknet. Please welcome Gideon Kaempfer.
Hi, everyone. Let's see if you can hear me. Okay, so the goal of this presentation is to talk about everything beyond recursive proving, but I'm not going to assume you know everything about proving or recursive proving. So I'll just begin with the basics and you'll follow me, I assume. So let's talk about the basics of a validity rollup. What composes a validity rollup? You have transactions. Sequencers select these transactions, define their order, and I'll use the term sequencer also for execution of these transactions. So if you're confused by based rollups where they separate the sequencing from execution, here I'm going to combine them. And they build the blocks. Once we have a block, the way a validity rollup works is that it proves the validity of the execution of these blocks using a prover instance and sends this proof per block to a verifier contract on Ethereum, on the underlying layer 1. And once that proof has been accepted, a state contract tracking the state of the rollup is updated with a new state. Together with the state update, we also add what we call state diff, and we may include also messaging between the layer 2, the validity rollup, and the underlying network. State diff, just to make sure you understand what I mean when I talk about state diff, is basically the update to the state of the rollup resulting from the executed block. Validity rollups do not need to transmit the actual transactions that they sequenced to the underlying layer. There's no such thing as fraud proofs or anything of that kind. We positively prove everything happening on a validity rollup. And as a result, we can send much less data to the underlying network in order to be able to reconstruct the full state of the layer 2. So a state diff is basically just the locations in the state that have changed and their values. So in this simple example, D has been changed into X. So the state diff of the transition from state 1 to state 2 is just a single element, change location 3 to value X. What does it mean to prove a block? So basically what we're doing is we're using the context of a proof in order to prove the statement that we have seen a valid execution from a given state A resulting in a new state B, and the resulting state diff between state A and state B is such and such. So the statement is the transactions were correctly sequenced and the input state results in the output state. What are we doing on layer 1 for the validity rollup? In this simple basic validity rollup, we need to verify a proof of a block, which can be costly in some cases. We need to publish the state diff, typically using blobs on Ethereum. And we need to update the state, which is typically some contract call of the state contract tracking the state of the rollup on layer 1. As long as the blocks are significantly large, this is fine. But if we want just to have a few transactions per block on layer 2 or quick finality, this can become quite costly. So the basic validity rollup is good if you have either very large blocks or you have a lot of traffic and then you can still have a short finality on layer 2. Or you have long finality, then it becomes less costly, but it's less effective because you have long finality. Enter recursive proving. Recursive proving intends to reduce the overhead of verifying the proofs per block. So let's begin with what recursive proving really is. So on the left-hand side, you can see the generic concept of proving. So basically, you have some statement and you want to prove that given given an input or a witness, if you like, there is a correct execution of this statement resulting in a given output. And what the prover does, it basically proves that the statement was run correctly on the input and that the actual output is the given output. The proof does not necessarily need to divulge the input, as we call it zero-knowledge proofs. But if you like to include some of the input in the output, you can just copy that within the statement. So how do we use this context, this concept to create recursive proving? Basically, we replace the statement with a new statement that just says, I verified 2 proofs and found them to be correct. So proof 1 with output 1 and proof 2 with output 2, you use a statement that performs verification, which is just an algorithm, right? So there's no reason that you can't build such a statement. And the result is the 2 outputs, the original outputs, you just copy them from the input to the output. So when we prove this statement, exactly like on the left-hand side, the result is a proof and the outputs that we want to generate, which in this case are output 1 and output 2. What does this mean? We've basically combined 2 proofs with 2 outputs into 1 proof with 2 outputs. Now we can use this construct in order to combine various statements, possibly totally different statements from different sources. If you like, we can prove statements from multiple rollups even, into a single proof and a series of outputs coming from the original inputs, or from the original statements, I should say. So in this diagram, you can see 4 different statements. There's no relationship between them. Each of them has their own input, creates their own output. And using recursive proving twice in this example, we result with 1 proof and 4 outputs. So what does a validity rollup with recursive proving look like? Very, very similar to what we had before. So you have the transactions, the sequencers, define the sequence, execute the transactions, and create blocks, just like before. In this case, let's say they accumulate 4 blocks. Then we can use recursive proving in order to prove these 4 blocks with 1 proof, as opposed to 4 proofs in the previous example in the basic validity rollup. And this proof is sent to the same verifier contract on layer 1. Then, for every block, a state update takes place on layer 1, on the smart contract that tracks the state of the rollup, and the state diffs per block are sent to layer 1. So using recursive proving, we've basically reduced the cost of verifying proofs on layer 1, but we still keep the concept of publishing state diffs per block and state updates per transition. So from state I to state I plus 1 takes place per block. It's less costly than before because sometimes a significant cost is on the verification of the proof. State updates are less costly, but the smaller the blocks get, the more significant the cost of these state updates become. So this allows us to improve, to reduce block times on layer 2, on the rollup, or if you like, reduces the need to perform large batching on the blocks on layer 2, but still, we'd like to optimize this further. Which brings me to beyond recursive proving, which is the topic of my discussion. We want to build something which we call applicative recursion. So let's define applicative recursion roughly in the following way. Here you see again the same recursive proving tree that we had before. We have 4 input statements. We combine them together into a single proof with 4 outputs. With applicative recursion, the difference from regular recursive proving is that here we're going to assume that all the statements come from a single application, so they have some kind of common semantics. For instance, these are 4 proofs of blocks coming from the same rollup. Then what we do is we use the same the concept of proving, but now for basically squashing the outputs together into a single output. So in this case, we'll have a new statement, which basically says, this is in the red rectangle on the bottom, basically we verify the last proof, so we make sure that the outputs are valid by using verification of this proof, and we perform a statement that is a valid combination of the 4 outputs into a single output. So the result is a single proof with a single output this time. So let's see what this output could contain, okay? So for example, if we're interested in aggregating state diff, here is an example of 3 state transitions. So we're moving from state 1 to state 2 to state 3 and eventually to state 4. In each transition, we generate state diff. So in the first transition, you can see that position number 3 has changed from D into X. In the second transition, we're touching positions 5 and 6. And in the last transition, the third transition from state 3 to state 4, we're changing position 3 again and position 6 again. So the result is the state called S4 on the bottom of the slide. But if you look at the resulting state diff between S1 and S4, there are only 3 changes. So there's no reason to transmit 3 state diffs with 6 changes, as in this example. So one of the things that we can do in the squashing proof, this final step of applicative recursion, is joining the outputs together into a single, more concise output. Now in reality, for validity rollups, it happens quite a lot that the same positions in the state are changed multiple times, even within a block, and certainly between blocks, especially if there are many, many blocks or large blocks. So this kind of aggregation is very important to improve efficiency of state diffs transmitted to the blockchain. But also other things can be done, and I'll go into examples in a moment. So now, a validity rollup looks like this. You have the transactions. As you know, they're sequenced and executed, put into blocks. For every set of blocks, we create a recursive proof. Then we do the applicative recursion because all these proofs relate to the same application, the same rollup in this case. So we can do that. And this single proof with the aggregated output, a single output, is sent to the verifier on layer 1. So we pay for verification just like we paid for verification in the previous example using simple recursive proving. But now, instead of doing a state update per block, we can do a state update per recursive cycle, if you like, for multiple blocks together simultaneously. So what does this look like? So we have the recursive, applicative recursion. Per recursion, we verify a proof, and per recursion, we publish the aggregate state diff in 1 or more blobs, and update the state on the contract that tracks the state of the rollup with a single state update that updates the state to the final state we've reached after multiple blocks. And of course, we can include messaging as before. So the more blocks we have per recursion, the lower layer 1 cost will be. And this basically scales infinitely depending on the latency you require to layer 1. This is actually what we are doing currently on our rollup called Starknet. What else can be done in this applicative squashing, or if you like, in applicative recursion? So the basic aggregation of state diffs, as I mentioned, is just a straightforward aggregation. But you can also do more sophisticated things. For instance, if you want to represent your state in a more efficient way, so utilize your blobs more efficiently, you can implement, for instance, a compression algorithm on this data. Just deflating the data into much smaller form, which allows you to include more blocks on your applicative recursion. Of course, eventually, when all the blobs fill up, you may reach a state where blob prices could go up, or you have more blobs than could fit in a single transaction and things like that. That is something you want to avoid, so that's a point where you want to cut off the applicative recursion, so it's not really infinite, as I mentioned before. In addition, as I mentioned, you can remove the need to do update states per block. And if you like, you can generalize this into a concept of segmenting a very large computation into multiple segments. So if you prove that you've executed a program from some state A to some state B, and then you've executed the same program or continuation of the program from state B to state C, etc., an applicative recursion or the squashing mechanism can ensure that you've actually proven the complete execution of this program from state A all the way through state C or Z or whatever. So this is the generalization of the concept of applicative recursion. And you may have more ideas here, and the more creative you get, the more interesting it gets. So basically, if you think about it, the whole concept of recursive proving, applicative proving, are a few examples of off-chain proving. So these are proofs that are never submitted to a verifier on layer 1. So basically, they're only submitted to a new statement that verifies them off-chain completely. And there are other examples that are useful in this context, and I'll talk about a few of these. So one example could be, for instance, for a privacy-preserving exchange, for example. So let's say you have an exchange on your rollup on the blockchain itself. Typically, exchanges that are on-chain, they expose the positions of their users. Some users are very sensitive to this information because it divulges trading strategies. So what you can do is basically have a user who knows their own position execute some order on their position while keeping the position encrypted on the rollup itself, or on the blockchain, if you like. So in this example, if I go over the diagram, you store encrypted positions on the blockchain. Every user is involved in the encryption of this position by using their own key. They can read the encrypted position, decrypt it, and then execute an order on their own position and encrypt the resulting position. Now, if they prove to a contract that executes trades that this would be the result of their encrypted position if, for instance, they get a little more ETH selling a little bit of Bitcoin, then a trading contract, or if you like, an exchange, can accept that proof without actually knowing the contents of the current position. So, of course, this does divulge some information because we are telling the exchange by how much we are selling and how much we are buying. But anyone looking at the position of a given user wouldn't be able to decipher the current strategy of this trader. So this is one example where proofs can be combined into a blockchain in order to create a more private environment by using client-side proving in this example. There are variants of this concept where we trust the exchange with our private information, and then all the positions can be encrypted and decrypted by the exchange as part of proving. But this is one interesting example that can also be implemented on rollups or blockchains, as long as you have a contract that can verify proofs. On Starknet, we have contracts verifying Stark proofs. We also have a contract verifying Groth16 proofs. So you have a choice of building your application on top of that on Starknet today. Another example is for scaling blockchains. And this will be my final slide, so for everyone pressed for time. This is a little bit more sophisticated, but the idea is, let's say I have a bottleneck in terms of the capacity of sequencing and execution of what's going on in the rollup. I want to outsource sequencing to someone else, if you like. Or I want to shard my layer, my validity rollup, so that different sequencers can run together in parallel, sequencing different parts of the rollup, or different contracts, if you like, some segregation of transactions. So in this context, what you see here is something that looks like two rollups, but they're actually the same rollup. So you have multiple sequencers, each executing part of the sequencing for the rollup, and proving this sequencing is correct using the validity concept, where the output of this proof is the state diff, or the changes to the state in the areas that they're responsible for. An underlying sequencer, which is the validity rollup sequencer, can verify these proofs, completely remaining on the rollup. These proofs don't need to be sent to Ethereum. And by verifying these proofs, this rollup sequencer can accept the state diffs coming from these various shards, or what we call ZK threads. And when we combine the state of all the threads, we result in a single state of a single rollup that can be, as in the previous story, transmitted to Ethereum with various kinds of proving, resulting in a unified rollup that has all the state computed by multiple sequencers. So here we utilize validity proofs in order to scale a rollup. That's it. I think I have 3 seconds left.
Thank you. We have now a few questions. Could you question? So I think the first question is how is aggregating state differs from multiple blocks, and is it better than increasing the block time itself?
Aggregating state is better than multiple blocks. Multiple blocks is better than having a single aggregate block. I'll put it that way. Why? Because what users really want is finality on layer 2, on the validity rollup itself. So response times go down, the smaller the block is. Of course, if we would wait for an hour to aggregate lots of transactions in a block, then we would have huge blocks and the basic validity rollup would work, but finality on layer 2 would be very slow. I also want to answer about proving cost. It's a good question because in the past people thought that proving, I remember back in 2017 or 2018, the number thrown at people was that proving a statement was something like 4 orders of magnitude less performant than actually executing that statement. At Starkware, I think our initial prover reached about 2 orders of magnitude, which is called the stone prover. And today we're talking about stew prover, where execution of the statement is almost the same as proving the statement. So the cost of proving has gone down very, very significantly. Well, it's not the same, of course. You still have an overhead. But to prove statements today costs very, very little. So all this recursive proving, for instance, is done within seconds, every recursive step. So you get a very quick finality even of the recursive proof, and of course that doesn't cost much.
Okay, we have still time. So what's the current transaction finality on Starknet, if you can?
Yes, currently on Starknet you get finality on layer 2 within 2 seconds.
2 seconds, wow.
And these 2 seconds will be preserved in a decentralized environment where actually block times will go down to 2 seconds, and we will continue to prove every block. So that's where we can go with this technology.
And maybe could this be used for cross-rollup communications through a shared prover?
Absolutely. In fact, in Starkware, I should say, today we already have a shared prover. It's called Sharp for shared proving, and we use it for many systems together. So we use it for public Starknet, we use it for private StarkX instances, which are layer 2 platforms for exchanges. We use it for app chains of Starknet, and all of these proofs are combined into single recursive proofs. Some of them are applicative recursion, some of them are regular recursion, and all of this is submitted in a single proof, attesting to a huge number of execution steps across multiple systems. So of course, this could also be used for messaging between different rollups.
Do we have any questions from the audience? No? Okay.